Now, suppose the usual thing, you have a function defined on A, B, and you have a tag partition. So now every subinterval has a distinguished point within it, which may be one or the other of the endpoints of the subinterval. We're going to quickly, but generally isn't. A Riemann sum is an expression of that form, where you go get the tag point, evaluate the function there, and then multiply it by the width of the subinterval in which the tag point resides. Okay? So the tag point ti here is between x sub I minus 1 and x sub I. The distance, or the length of the subinterval from x sub I minus 1 to x sub I is delta xi. That's the width of the elementary rectangle. We're going to say the height is the function evaluated at the tag point ti. So we add all those up over every subinterval, and that is a Riemann sum. Okay? And then by analogy with the Cauchy system, now we've seen how this works. Given epsilon greater than 0, there exists a delta that depends on epsilon and m. And a real number L, the limit, such that for any tag partition whose norm is less than the delta, it is true that the absolute value of the Riemann sum minus the limit is less than epsilon. We say that the Riemann integral of f exists and equals that limit. And we denote that by an R in front, to say that we have used the Riemann construction to make that okay? Listen to me. Oh, you impressed the hell out of me. They love one time. Oh, he's been paying attention. All right. Here is the exact same definition. Well, it's not the exact same definition. It's the same concept defined equivalently, but using the notion of refined partitions instead of epsilons and deltas. Well, I mean, we use epsilons, but we don't use delta. It's not an epsilon delta group. It's an epsilon refinement. How's that? So what's the deal? Again, we have the tag partition, and we have the notion of order with a partially ordered set of partitions of A, B, for a pre-assigned epsilon greater than 0. If there exists a partition P of epsilon and a real number L, such that whenever you have a partition finer than P sub epsilon, so this magic partition, once you get past it, that the difference between the sum that you have and the limit is always absolutely less than epsilon. And f is Riemann integrable with L. Okay? So this is slightly different than having the norm, where you insist that the norm of the partition be less than delta. Here there is no delta. It's a magic partition. Once you get past it, in the order of partitions, if then the absolute difference of your Riemann sum and L is always less than the pre-assigned epsilon, you say the function is Riemann integrable on AB and equals L. Okay? Okay. All right. So, next. I think Thomas Stieltjes was in Czech, and living in the latter part of the 19th century. He didn't live terribly long. Pulling down the average age of mathematicians upon death. I think it's grossly higher than the population at large. Abel, Galois, Stieltjes notwithstanding. Mathematicians tend to live very, very long. So keep that in mind as a career strategy. Well, the idea that Stieltjes had was to get away from just the length of an interval being delta epsilon. He said, let's invent a more general mass function. It's as if we have the x-axis as a wire and we coat it with something that makes it heavier in a variable way. So the mass, the length associated between the partition point x sub I minus 1 and x sub I is no longer going to be just the difference. It's going to be the mass function alpha of x evaluated at I, and then also evaluated at I minus 1, and the difference taken, right? So if you have a rapidly increasing mass function, you know, the little rectangle back there between 1 and 1.1 is going to be a whole lot lighter and less significant in its contribution to the Stieltjes input than the one out there between 10 and 10.1, right? Because that mass function is going up. Later is more important in that situation. Okay. This also opens the way to easy proofs about integration by parts and some substitution theories. If you've ever tried to prove that from scratch in analysis, I doubt if you got to it in analysis 1 or even analysis 2. Did you prove integration by parts religiously? I mean, every last little detail covered. Did that. Look at it. I'll bring a proof in a second. We'll see if we can struggle through it. It ain't easy. There's just a bazillion details you have to worry about. Anyway, having the flexibility of that alpha function is very helpful because d alpha turns out to be alpha prime of x dx, right? So you get some play there. It's helpful when we can start to prove things about the substitution theorem for integration, you know, which we just blow over in Calc 2. We're going to be teaching that shortly in Calc 2. We just do it, you know. There's no justification. It's one of those, you pluck it out of the air. Here you go, do it. But when you pop the hood and get under and start proving all this stuff, it's not so easy. Okay. So what you do is you create a delta alpha of xi, which is the weighted length of that interval, okay? And then you put that into the Darboux sum, upper and lower, right? These are Darboux sums with, instead of delta xi, delta alpha of xi, aren't they? So I have a lower Stieltjes sum. It depends on the partition, it depends on the function, and it depends on the particular weight that you're placing on the x-axis. The weight determines the one dimension of the rectangle. F determines the other dimension, and the partition determines where all the rectangles are located. So the lower and upper Stieltjes sums depend on those three things, right? Once again, we do the same trick as we did with Darboux. The lower Stieltjes sums, we take the supremum of those as the partitions vary. The upper Stieltjes sums, we take the infimum of those as the partitions run all over the place. And if those two things come together, we say, aha, the common value is the Stieltjes integral of f with respect to the mass function alpha on the interval AB, right? So it's a reprise of the Darboux formalism with a general weight applied to the x-axis, right? Okay. So that's what a Stieltjes integral is. So you go through the same thing. You get the upper Stieltjes integral, the lower Stieltjes integral. If the weighting function alpha of x is equal to x, what do you have? You have the Riemann integral, don't you? Or the Darboux integral. Same thing. Darboux equals Riemann. But if the weighting function is just x, you know, that's it. Then delta alpha of xi equals delta xi. The weighting functions cannot be totally arbitrary. First of all, you can't stand them being negative, right? You don't want to have positive weights here and suddenly negative weights out here. So when you do the integral, you get cancellation. Can't have that. So the weighting functions, the mass functions, have to be non-negative. Another thing that has to happen, they have to